This is the final frontier. Chapter 8, Section 6. We'll be looking at trapezoids. This is our last foray into quadrilaterals. So, believe it or not, we've come to the end of the road. Let's get to it. Definitions, as always. Take a look. A trapezoid. A trapezoid is a quadrilateral with exactly one pair of opposite sides being parallel. And notice, exactly. If you allow for two, then we're back to being a parallelogram, and well, what's the point in that? So let's talk about some just basic vocabulary here. A and B are said to be base angles, with the base being AB on this case. D and C are said to be base angles as well when compared to base CD. The other two sides are known as legs. So again, just some basic vocabulary for you. Notice A, B, and then D, C are bases, and they are the ones that are parallel to each other. So again, just some terminology. Isosceles triangles are what people typically think of when they think of a trapezoid. Though, for example, I could draw a trapezoid, say like this. This would also work as a trapezoid with my parallel sides being here and here, those bases, and then of course my other two legs, one being significantly shorter than the other, but that would also work. But again, when people think trapezoid, they tend to think of the isosceles trapezoid, and the only difference in the two is where we have an isosceles trapezoid, those legs are the same length. In other words, they are congruent. So a lot of what we'll focus on will be with the isosceles trapezoid, though know that typically a trapezoid does not have legs that are congruent. It can, but does not have to. All right, so that's it. All right, let's look at some theorems. Theorems, as always. Take a look. This first one here. And I don't like the way this was done, kind of helter-skelter. There we go. So the top one, both pairs of base angles of an isosceles trapezoid are congruent. In other words, if we have an isosceles trapezoid, then both pairs of base angles are congruent. So notice here's just a nondescript isosceles triangle. A and B, that pair of base angles is congruent, and C and D, that pair is congruent. So that's one theorem. The second one, so let's number them here, theorem 1, theorem 2. Our second theorem says that the diagonals of an isosceles trapezoid are congruent. All right, well, let's talk about each one of these sort of in turn and see what we can do. And I'm going to swap out from my pen for pencil, because we're going to use this diagram down here. This diagram is fine, but it's kind of busy. So let's use this one. Now, a lot of times when people are asked to prove one of these, they tend to reference the other. So trying to prove the diagonals, well, they reach for the base angles being the same. Or if they want to know if the diagonals are congruent, then they reach, and so on. So what we're going to do is we're going to try to break that chain. We're going to try to prove each of these independently of the other. So diagonals of a trapezoid being congruent, let's start there. So in other words, that B to D is the same distance as it is from A to C. Let's see what we can do. First off, I'm going to draw an auxiliary line from A to side DC, and I'm going to make certain that it's a height, all right, an altitude, however you want to word it. It's perpendicular. We'll do the same over here, from B down to CD, and again, making it perpendicular. Cool. So since we're dealing with an isosceles in both of these cases, we know that AD and BC are the same. That's given to us. All right, cool. Now that I know that, let's try a couple other issues here real quick. First, since this is a right triangle, both of them by definition, they have AD and BC in common. AD and B, or excuse me, A to not D, A we'll call this E, we'll call this F. A to E and B to E are also the same as each other because they are simply the distance between a set of parallel lines. Obviously, that distance remains unchanged. And that's a side-side angle situation with that right angle, so that won't do. We can use Pythagorean theorem, however, to get ED and FC being the same. Notice with their right triangles, two of the sides being the same, that third is automatically going to fall out. So let's go ahead and mark those. Pythagorean theorem allows us to state that. Excellent. So a quick review. This is what we're trying to prove, our two here, and here's where we're at. We've got these two right triangles on either end of our isosceles trapezoid that are indeed now congruent. So we can say that all the parts are congruent as well. So right off the bat, base angles, we're good. Obviously, I've got this angle here and this angle here being congruent. Awesome. We can then take that a step further and say that these smaller angles are then congruent to each other. Of course, adding on the 90s, that means A and B are congruent to each other as well. Cool. So we can check that one off. Let's talk about the diagonals. Well, now that we've shown that this first one is good, independent on its own, without having to go round and round, let's erase those real quick. I'm going to go ahead and keep, remember we started off with these right triangles. I'm going to go ahead and keep D and C in here. We know that they are now congruent. We're going to go ahead and draw our first diagonal in here, our second diagonal in here. So we've got our two triangles. Obviously, they have CD in common, so let's mark that. Angle C and angle D are the same, so they've got an angle. And then AD and BC are the same, so that's a side, angle, side, side, angle, side. Therefore, the diagonals are also congruent. Cool, so cool. We've proven both. And again, I didn't use the other necessarily to get that done. A lot of people do. Remember, what we did here is we started off with these right triangles. We proved that they were congruent, got those bottom base angles figured out, of course, by definition, or not by definition, by, oh, I can't think of the word now. Oh, that's terrible. Oh, process of elimination, or not process of elimination, goodness. By deductive reasoning, there we go. It's going to get to it eventually. We've got that A and B, of course, are there, and then we've got our final right angles as well. So, awesome. Proving these are the same, and these are the same, and we're good. Excellent. All right, well, let's try this next one. This should be somewhat familiar, reminiscent. This idea of a median or a mid-segment, as we called it with our triangles. And just a quick reminder of how this works. We're going to grab the midpoint of each side and simply connect it, and that gives us the median. When we were dealing with triangles, we could call them medians. We could also call them mid-segments. So again, this should be somewhat familiar. And what we're going to do with these is the following theorem. It says the median of a trapezoid is parallel to the bases, and its measure is 1/2 the sum of the measures of the bases. In other words, if I took AB and took its measurement and added it to DC, whatever that measurement is, and then took half of it. So in other words, we're finding the average. That EF, that distance, is the average, the in-between point of A, B, and DC. So for example, if AB was, I don't know, making this up, 3 and DC was 5, then cool, EF has to be 4, all right, the average in between. So one way to prove this is to use coordinate notation. So for example, I could put my 4 vertices down, right? And let's say, for example, that, let's see, we'll label them here, A, B, C, and D. There you go, that way it matches our figure. Let's go ahead and find each of those locales, making sure we keep it as a trapezoid, and then we can see that, hey, this distance compared to those will indeed be the midpoint. Let's see, we're going to go 2x over, and we'll say, actually, let's change that. Let's say that's 4x over. We're just making this up. 4x over and 2x up. There we go. So this one will make just the opposite of that to keep things the same, a negative 4x and then 2x. All right. Down here, again, I'm going to try and keep the numbers even if I can. Let's say, just making this up, let's say this is 6x and negative 2x. And then over here, negative 6x and negative 2x. Cool. Just to give it some locales, not specific locations, but general locations. Awesome. So we need to find our midpoints. All right. So in other words, if I take this, add them together, divide by 2, that would give me 5x. Add together, divide by 2. Of course, that's 0. Add together, divide by 2. That would be negative 5x. Add together, divide by 2. That's 0. Cool. So there are the locations. So if I wanted to find the distance here now between my points, it's easy. They're all horizontal. So I've got 8x up top. I've got 10x in the middle. And then I've got 12x at the bottom. And sure enough, if I rearrange these, 10x is equal to 8x added to 12x over 2. And then, of course, we could rework that and whittle it down to something more like that. But again, we can do it with coordinate geometry as well to show that, hey, that is indeed that mid range. And again, a little bit of algebra, we're there. Let's try some examples. All right. So again, back to some coordinate notation here. We're going to try and verify that the quadrilateral is a trapezoid. So that's our first step. And then we're going to determine whether the figure is isosceles or not. So again, we're going to do kind of a rough sketch to start this off. Again, I didn't put a grid on here on purpose, just so that we can rely on things like slopes and distances, midpoints if we have to, that kind of thing. So -3, 3, so that's A. B is at -4, -1, so there's B. C is at 5, -1, so there's C. And then D is at 2, 3. Cool, we'll play connect the dots here real quick. All right, well, first off, is it a trapezoid? Well, I think we can safely say yes. A to D, that slope is going to be 0. Notice when I subtract the y coordinates, we'll get 0 over some number, and that means our slope in this case is 0. It's a horizontal. For B to C, we get the same thing here. Notice the y's are the same, so -1 subtract a -1 zeros out. So our slope here is also 0. And if you look for A to B, that's a positive slope. For D to C, that's a negative slope. So cool. We definitely have a trapezoid, so we can check that off. The question, of course, is this an isosceles trapezoid? Well, let's see what we got. If we're looking at the distance from A to B, let's see, difference here is 1 plus difference there is 4. So I'm looking at the square root of 17 as the distance between A to B. All right, let's do the same thing for D to C. If we subtract that, we would get 3. Difference there is, what is that, 4. So we get 9 and 16. That's 25. Square root of 25 being 5. So yeah, notice in this case, let me double check that math there. 1 and 4. Yeah, I did that, right? Just double checking. So yeah, it looks like in this case, no. My drawing might appear isosceles, but no, the difference in the distances here, this is a lot closer to 4. That's 5 exactly. So no, not isosceles, but definitely a trapezoid. All right. Here we're just finding our averages again. So notice we could say DE, for example, is some unknown. We'll call it Y. So if I take Y and add that to 32 over 2, we should get 20. All right, well, we can solve that pretty quickly. Y added to 32 equals 40. And then subtract the 32 from both sides. In this case, Y would equal 8. So we can write that in. Fair enough. And then over here, same story, not a big deal. So we'll call this X this time. So X added to 26 over 2 equals 15. Multiply both sides by 2. X plus 26 is 30. And then go ahead and subtract that out. X is 4. And there it is. So this is the kind of work that we'll be doing today. Again, a little bit of coordinate work in there. Again, making sure we understand our median work. And again, folks, when it comes to the theorems, make sure that you are keeping good lists of those for your, whether your proof project or just for your general proof cheat sheet. That way, as we're doing different proofs throughout, that you've got some idea of not only what they are, but how they work and what they actually prove. So that way, when you're doing proofs, you're pulling the right item. All right, if you have any questions or concerns, please bring them with you to class. Otherwise, have a good day.